Hi, welcome to this webinar. My name is Thomas and this is Liliana, and we're both applications engineers at the MPS office in Barcelona. Today, we come from the MPS Now Lab, which we've created to help solve any problems that you may encounter using our products. In this webinar, we're going to be talking about the new digitally programmable converters, the MPQ888x family. Let's move on to the presentation. So as I said before, we're going to be talking today about the MPQ888x, the power of analog converters and the flexibility of a digital device. First things first, a bit of housekeeping. Please remember that this webinar will be available for on-demand streaming at a later date. But for now, please remember that you're all muted. So if you have any questions, feel free to put them in the Q&A button, and we'll try to get to as many of them during and at the end of the presentation. With us today are Jens and Samuel, field applications engineers for Central Europe, and they'll be helping us answer any questions that you may have. So what we're going to talk about today is the MPQ888x family. We're going to start with an introduction into converters, and then we're going to talk about our new digitally configurable buck converters. Then we're going to talk about our software, Virtual Bench Pro, which helps you monitor and set up your device. Then we're going to show you our setup and do a live demonstration of how the virtual bench and the converters work. Then finally, we're going to be answering your questions. So let's begin. Power converters can be found in a wide variety of electronic devices. They're necessary for ensuring constant, controlled voltage levels that can efficiently power electronic systems. Power converters can step voltage both up or down, but in this presentation, we're going to focus on step-down converters, also known as buck converters. Here you can see a basic schematic of a buck converter. This converter uses switches, inductors, and capacitors in the power path, highlighted in red, to change the input voltage level to a lower value. The main goal of a power converter is to ensure that the output voltage is stable, regardless of any changes in the system, such as variations in the load or in the input voltage. This means that the converter needs a second path, called a control path, that can compensate for any of these variations and maintain a stable output. In order to increase or decrease the output voltage, the controller changes the switching MOSFET's duty cycle, which is defined as the ratio between the time the switch is closed and the total switching period. If the duty cycle is close to 1, then the switches are on for longer than they are off, which means that the output will be closer to the supply voltage. On the other hand, the closer the duty cycle gets to 0, the less time the switches are on, and so there will be less voltage at the output. The converter shown in the slide uses current mode control, which makes use of two loops, one for voltage and another for current. Even in this simplified control loop schematic, you can see that it is made up of many different elements. Any change in these components will have a significant effect on the controller's response. For example, a change in the value of the resistor in the schematic will result in changes in the response that the system has to variations in the output voltage. Now, when designing a power converter, designers seldom have to implement the switches, the comparators, and many other elements which take up a lot of board space. Instead, they can buy a controller IC and modify its response by changing the value of the passive components connected to the different pins in the IC, as you can see in this circuit on the slide. However, during the design process, they often have to tweak many aspects of the converter's control loop in order to optimize it for their application. This is a slow and painstaking process of soldering and desoldering passive components, such as the resistor we saw before. It also has the negative effect of taking up extra board space, given the necessity to use layouts and components that can be easily manually substituted. One possible alternative could be changing from an analog control loop to a purely digital one. But this would also require more complex mathematical formulation and would result in a slower control response that would take up more board space than the analog implementation. The solution that MPS has come up with is a middle ground between the two. We've added two communication pins to the controller, through which the user can digitally select the converter's parameters. This allows us to keep the benefits of analog converters, such as the fast response and higher power density, while reducing board space, cost, and design time. These converters also allow for on-the-fly changes in parameters and monitoring, as well as enhanced customizability. And another benefit of eliminating external passive components is the simplified hardware structure, which increases reliability and enables better failure mode error analysis. The communication with the controller is done through the PM-bus I2-based protocol. This communication interface allows designers to input control parameters and monitor the controller's operation, receiving values for output voltage, current, switching frequency, and possible fault flags. It even allows designers to control how the system responds to these faults by modifying the response and retry settings. So now that we've introduced these digitally programmable converters, let's move on to a more specific case, the MPQ888x family. This IC family is made up of 3 digitally programmable converters. The 8883 is designed with a maximum 45 volts at the input and 12 volts at the output, and can output up to 3 amps of current. The 8880 has a larger input voltage range, up to 60 volts, and an output voltage of up to 20, with a current of 4 amps. It can be connected in parallel in order to increase this output current, with a maximum of 4 parallel converters outputting 16 amps. Finally, the MPQ8886 can output 24 volts and has a maximum current of 6 amps. This converter has 2 channels, which can work independently, outputting 3 amps of current in each channel, or it can work together. These channels can work together for currents up to 6 amps. It can also be connected in parallel with another 6 IC to get a maximum of 36 amps. All these converters have more or less the same amount of configurable parameters, but both the 8880 and the 8886 are AEC Q100 qualified, meaning they're perfect for automotive industry applications. Now, for the rest of the presentation, we're only going to talk about the MPQ8886. I'm not going to go again into too much depth on the characteristics, but it's important to note that it has a wide input voltage range, a programmable output voltage and switching frequency, and a large variety of protections, including overvoltage, overcurrent, and overheating, which can also be digitally programmed, as well as the multiple operation modes, which we'll talk more about later on. What's really important to remember is that the control path for this converter, as for all the converters in the 88X family, is still entirely analog. As you can see in the block diagram, there are still the same components as in a traditional analog control loop, such as the voltage divider, an OTA, passive components, and slope compensation for the current loop. The digital core, highlighted in blue, is the communication interface that will allow the designer to control and monitor the converter's operation. This information is sent and received through the SCL and SDA ports, saved in the I2C registers, and converted into analog signals such as reference voltages. The MPQ8886 also converts the analog signals it senses from the converter into digital signals that it can send back through the computer through the same communication interface. Now, all parameter values are saved in the programmable memory, so the operation of the controller won't be affected if communication is severed. In fact, these communications could be used as dummy analog converters without using the digital communication interface, just with the preset factory parameter values stored in the memory. In the slide, we've highlighted different aspects of the controller that you can modify, such as protection references, compensation parameters, control mode, or timing. As I mentioned before, one important aspect of the MPQ8886 is that it can be set to work in 4 different configurations. Now, first is the dual output mode, which provides 2 separate outputs, one for each channel. An output current will be of 3 amps, so it's kind of like a 2-in-1 converter. If your application needs a higher current, then there are 2 options. The first configuration is the dual channel single inductor, which parallels both channels to handle up to 6 amps of output current. Only one inductor is used in this configuration, so both channels are in phase, but only using one inductor will save up board space. Now, if you need an increased output current, but you also require a low ripple voltage, then you can use the dual phase single output topology, where each channel has its own inductor, and the outputs are externally connected to supply the increased current. Using multiple inductors allows for phase interleaving, which offers increased output current and low input and output ripples, but it comes at the expense of more board space because you're using more inductors. Now, finally, if you need an even higher current, parallel operation allows for the parallel connection of up to 6 MPQ888x converters, which will result in a total maximum current of up to 36 amps. Here you can see some of the PM bus commands that the user can find in our product datasheet. These PM bus commands can generally be grouped into several categories, such as compensation and protection, to name a couple, because if you look at the datasheet, you'll see that there's approximately 20 pages dedicated to the programming of the IC. Now, programming these registers can seem tedious, but in a few seconds, we're going to show you how to program different values for some of these parameters using our graphical user interface, VirtualBench Pro. So, manually programming these parameters could be complicated. But to make the communication with the controller easier, MPS has developed a software interface called VirtualBench Pro. This tool allows the user to easily configure parameters and monitor your converter through automatically generated waveforms for magnitudes such as the input and output current, the voltage, and the temperature. For more advanced parameters, such as protections and compensation, we also offer tips and guidance so you know how each parameter affects the operation. It also lets the user evaluate disconnected MPS devices using the offline mode, so you can get a head start on programming your device even before your evaluation board gets to your office. Now, the measurement setup is also really simple. As we'll show you in a few moments, all you need to do is connect your controller to a voltage source and an electronic load, and then connect it to the PC via the USB to PM bus dongle, which comes with the evaluation board for all the controllers in the MPQ888x family. All you need to do then is set up the VirtualBench tool and configure your device, as we're about to show you. So, what Liliana and I are going to show you is how the VirtualBench tool can change different parameters of the IC and how these changes in parameters affect the controller. So first, we're going to configure the basic parameter, such as output voltage and switching frequency, and then we're going to move on to more advanced parameters, like protections and compensation loop parameters. First of all, however, Liliana is going to walk you through our measurement setup.
Okay, thanks, Tommy. So let me show you our setup. Here we have an input voltage source, an electronic load, and oscilloscope. We also have the evaluation board for MPQ888x. So here we have the IC. In this case, we are using single phase, single output configuration, topology configuration. Here we have the inductor and the output capacitor. In this pin, we have connected the input voltage source, the output of the converter, and here are the connection pin, the communication pin. So the two wires that come from the I2C communication device. We also have connected a probe to the switch knob of the converter. We are also measuring the output voltage of the converter and the output current of the converter. So let me power on the IC. So in the scope, you can see the switching signal, the output voltage of the converter, and the output current. The switching frequency is about 600 kilohertz, and the output voltage is about 6.5 volts. The output current is 3 amps. So now Tommy will show you how to program new value for the IC.
Okay, so back on the computer, when you open VirtualBench Pro, this is the first screen that you'll see, which allows you to create a new project or open an old one. We're going to create a new project. Now, to add a device manually, all you need to do is select it from the list of devices, and then select the address with which the I2C protocol, which will communicate between the computer and the evaluation board. In our case, we've selected the 07 address. Now, once you open your device in the System tab, you'll see the following data. This allows you to monitor the basic parameters of your device, such as the input voltage, the input current, and the output voltage, the output current, and the temperature. Now, as you can see here, only one channel has an output voltage. This is because, as Liliana said, we're using the single phase and single output topology. If we had multiple devices, we could keep an eye on them simultaneously in this tab. But if we want to modify it, then we can go into the device tab. Once we go into the device tab, the first thing we should do is get the basic parameters that we already had installed from the non-volatile memory, which we're going to do, and make sure we clear all the faults. Okay, so now let's look at the parameters. The first ones in the top are the basic parameters. These include the output voltage, the voltage divider, and the switching frequency. So as a quick introduction to changing parameters, let's look at changing the output voltage. We simply delete the value that we have and insert a new value, which is in the range specified by the VirtualBench Pro. In this case, let's put 3 volts in as our output voltage. Then we just write it into our volatile memory, like so, and we can see here that our new output voltage has changed. But if we want to look at changes outside of the VirtualBench GUI, then let's have a try at changing the switching frequency. So what we're going to do is we're going to increase our switching frequency from 600 Hertz to 1000 kilohertz. Now, as we do this and we write it into the volatile memory, you can see in the scope how our frequency has changed. Now, if we get our values back to how we were at the beginning and clear the faults again. Now, in the monitoring window, you can see how these values have changed. Underneath, we have several other tabs. These include the fault tab, which you've already seen, and this indicates possible faults that occur, which you can clear using the clear fault button. Next, we have the automatically generated waveforms, where you can keep an eye on the real-time modifications in your values. And it's also very easy to take away any parameters that you may not be interested in. Next, we have the register map, where you can see all the registers that I mentioned previously and the values that they hold. And then finally, we have the log panel, which stores all the modifications you make to the device, which will make it very easy for us to help you if you run into any problems. Now, let's move on to the advanced parameters. We'll begin with the PWM tab. This allows you to modify PWM parameters, and this is very useful for reducing your converter's EMI. Next, let's move the protection parameters allow you to modify the thresholds and the response and the retry settings for your different protections in your device. For an example of this is the input overvoltage limit. Right now, we're supplying our IC with approximately 12 volts. So if we were to change this value, which is the threshold for this protection, to a value below this, say 10 volts, and we were to write it into our converter, we would see that immediately a fault appears. And if we go into the waveforms, we see that the converter has stopped functioning. If we want to repair this, we just simply reset the original values by reading the non-volatile memory, and the converter is operational again. Then we just clear the fault again, and everything is as it was. Now, finally, let's look at the compensation parameters. This may be one of the more complex areas to configure in the IC. So we've added help that will allow you to see how the parameters that you modify affects the converter's operation. Now, to show an example, we're going to modify the resistor, RTH, and Milana is going to show you how we're going to look and how that affects our setup.
Okay, thanks, Tommy. Now we are going to perform a load transient from 3 to 1 amps and see the main signal of the converter. Here you can see the switching signal, the output voltage, and the output current of the converter. You can see it an overshoot on the output voltage, and after a short period of time, it will recover the output voltage setting. So now we are going to apply the same change, but change one of the parameters of the control loop. So I want to keep the output voltage waveform in order to compare with the next test. So now we are going to apply. Tommy will program new value for the control parameter.
Yes, I just simply select from the drop-down list the new value for the resistor and write it into the volatile memory. And now,
if we apply the same chain from 3 to 1, we can see the output voltage of the converter have an overshoot. In this case, more greater than the previous one. So VirtualBench allow you to a fast evaluation, customize device performance, protection limits, and so many other features. So now we can move on the next section, Tommy.
Yes, well, now we're going to move on to the Q&A. So that's all from us. And we're going to answer any questions that you may have. Thank you very much for your attention.